So today we move on to a different topic. So we've been working on the semantics, we're doing lexical analysis. So today we move on to the next stage of the compiler process, which is syntax analysis. And note I'm taking attendance using an extension. So it shows exactly what time you joined and how long you're in the call. And only those of you who remain in the call for at least 1.5 hours will count as having attended the class. So inform your colleagues, those ones who keep logging in and off, it will show. And only those who meet a minimum of 1.5 hours in the class, in the call, will be recorded as having attended. So let's just go straight into syntax analysis. We have got a bit to go through, although largely it's a refresher. Um, we'll do that. Okay. So we know the stages that we need to go through. So we start from the source code, we have the lexical analysis, then we go to syntax, semantics, intermediate code generation, optimization, code generation, and then target architecture specific optimization. And finally, we have the machine code. So we're already comfortable with the first stage, which is lexical analysis. And I hope you're ready for your presentations tomorrow. Your assignment is due today on the scanner. So we move on to syntax analysis. And from what we had said last time, we know that the role of the parser, which does syntax analysis, is really to try and figure out the structure that the token stream from the scanner, what structure does it have vis-a-vis the grammar for that language. So assuming that is the code, the source code, we of course expect to get, we just process it as a character stream from left to right, which is what your scanners are currently doing. And the output of the scanner gives us a token stream. So we're able to know what tokens have been identified in the source language. So in this case, we have the token file, we have the parentheses, we have identifiers, and we have operators. So this becomes now the input to the syntax analyzer or the parser. And the role of the parser is to try and map the token stream to a structure that can be derived from the grammar that defines that language. So in this case, this parser is able to generate a while statement. So, and you can see it's a tree. We have the while tree, and we have the positions as needed. So this follows the grammar. So once able to do this, then we say that the source code or the token stream that has been given is syntactically correct. Right now, we are not able to detect any logical errors, but in terms of the grammar, we are happy that it follows the rules of the grammar, and that's why we're able to generate a parse tree. So for an example where we expect a syntactic error, so in this case, we have this as the source code. So the scanner will just generate the tokens, and all the tokens are valid because we're able to associate the tokens with the lexemes. But then this parser generates an error because it's not able to associate the token stream with a structure from the grammar for this language. So really that's what the parser is supposed to do. Receive the input from the scanner, check whether that input is generated by the grammar by ensuring that you can come up with a parse tree. If yes, accept. If not, generate an error, a syntax error. Okay. So what is syntax analysis? So after scanning, which is the lexical analysis, we generate a series of tokens. And the role of syntax analysis is to interpret what those tokens mean. And by saying we're interpreting, basically, there are two goals here. The first one is to identify the structure that is described by the series of tokens. And here, of course, the structure is asking, are we able to generate from the start symbol of that CFG, draw a parse tree or come up with a parse tree of which tokens and which non-terminals and terminal symbols have been used up to when we get the leaves at the bottom of the tree. So we have a complete parse tree. And that means we have recovered the structure that has been used for the token stream. Else, if that doesn't work, then generate an error. So this will be your next task. Once you're not done with your scanner, the next thing is to build the syntax analyzer. So you need to start now really listening to what the task of syntax analysis looks like, what are the goals, and you start figuring out how you then interface from your scanner to now process the tokens as they come in. So pictorially, we have that. So we have the parser in the middle here. The two inputs that it uses, of course, the first one is the context-free grammar. You've already come up with a mini grammar that you're using for your project. So there it defines all your non-terminals and terminal symbols and the rules that derive a particular non-terminal to a terminal symbol. So that is the reference that the syntax analyzer has. And then it receives a token stream from the lexer. And its work is to just determine if S is in the language of the grammar. In other words, can we uncover the structure starting from the start symbol of that grammar to the token stream that we have gotten from the lexer? If yes, we accept. If no, we generate appropriate error messages. So syntax analyzers are CFG acceptors. And I think you remember what a CFG is, although we're going to quickly do that. So they accept a CFG and use that CFG to determine whether the token stream from the scanner is actually forming a valid sentence or valid string in the grammar of that CFG. If at all, we can get a derivation from the tree. So in terms of understanding the syntax analysis phase, we're going to go through the formalisms for syntax analysis, the same way we did for scanning. We talked about regular languages. We refreshed our minds on regular expressions, deterministic FAs, NFAs, and converting NFAs and all that. So that was the bit that comes for lexical analysis. So we're going to do the same thing. What are the formalisms for syntax? So CFGs, derivations, the notion of concrete versus abstract syntax trees, and the biggest problem for a syntax analyzer, which is ambiguity. And then we're going to look at the different types of algorithms that are amenable to us to build our syntax analyzers. So we have top-down parsing, we have bottom-up parsing. So we start with the formalisms. So this is just a refresher. We already know when we're talking about scanning, the alphabet is basically a set of symbols that act as letters. And a language over a certain alphabet is basically the set of strings that can be formed by combining symbols from sigma. So when we're building our scanner, basically we're using either ASCII as our alphabet or Unicode characters. And then we have rules that show us, and these are regular expressions that show us how we combine the alphabet into valid tokens, or rather into like symbols that we associate with the tokens. So when we are parsing, now we can think of the alphabet, which is what the unit from which we form the units that we are trying to make sense of. In this case, we think of the token stream as the alphabet for the parser. So it only recognizes tokens and tries to figure out the structure. So we already know the limits of regular languages. And I remember what we did in the year 2 course on automata theory. We said that regular languages, or rather we have regular expressions, DFAs, and FAs, used to describe regular languages, but we say there's a class of languages that cannot be expressed using regular expressions because they are not regular. And if you remember, it was because regular languages, or even the tools that we're using like DFAs, etc., do not have a capacity to count. So there are many things that cannot be expressed using regular expressions. Okay. So for example, if you're trying to confirm that parentheses are matching, that there's a left for every left parentheses as a matching right parentheses, you can't do that using regular expressions. Okay. And even if you're trying to check nested block structures, you cannot do that with regular expressions because now that is more than a regular language. So these are context-free languages. And that's why we said we needed a now more powerful formalism to represent those class of languages that are not regular. Okay, and this is why now we introduced CFGs. So I hope you all remember that. So this is stuff we already know, so I'll move pretty fast. So a CFG is basically a formalism for defining context-free languages. And this is a superset of regular languages. So CFGs can define both regular and context-free languages, but not the other way around. The formalism for regular languages cannot be used to define context languages. So just refresh our minds. So this is an example of a CFG. So you take the language of arithmetic expressions. Supposing we want to describe all the legal expressions that we can have, that is addition, subtraction, multiplication, and division for now. There are many ways to express that CFG, and this is one example. So you could have our non-terminals here. We could say that expression is written as int. So in this case, whatever is in blue and small case is a terminal symbol. Whatever is in red and uppercase is a non-terminal symbol. Then the other option for expression is that an expression can be written as an expression, an operator, an expression, or an expression in brackets. Operators, we have 4 different types. Operator can be written as a plus, as a minus, as a times, as a division. And then now what we do is that once we have the CFG, we're basically trying, once we get our input, our token stream, which would be coming now from the scanner. So scanner in this case is saying there's an int, token times, token left parent, token int, token plus, token int, etc. The role of the parser now is to try and figure out which sequence of production rules from this CFG generate this string. Okay. So in this case, we'd say, here's plus, op can be written as plus. So we now have int times int of int, and then we write this in. This expression is written as int, and this expression written as int, and then we have this expression written as int, and so on and so forth, up until you go back to the start symbol. And once we're able to do that, then we say that the input to the parser is actually a valid string according to the grammar for that that the parser is based on. Okay. So this is another example, and it just shows that you can just we just have int division int. You're still able to figure out that this must be the structure that has been used to generate this, so we say it is a valid expression. Okay. So just as a refresher, a context-free grammar, we said is a 4-tuple model. First, we must specify the non-terminal symbols, which we also call variables. We have a set of terminal symbols. We have the production rules that say how we rewrite each non-terminal into either a sequence of terminals or a combination of terminals and non-terminal symbols. And of course, we must always specify the start symbol so that we know exactly where the parse tree is going to be constructed from. So in this case, we have 2 non-terminals, that is E, and we have 1, 2, 3, 4, 5, 6, 7 terminal symbols as shown in the graph. Okay. So here we're basically saying, just to remind ourselves that you can write it out in where you have a production for each different, you write each production in its own line, or we can use the shorthand where we combine all the productions for each non-terminal together using the OR. So A can be written as either int or E of E or E into brackets. Op can be written as either plus or minus or times a division. So these are equivalent, only that maybe it's stylistically we prefer this, or the shorthand is also okay. Now, one thing we must remember is not to confuse the notation for regular expressions with the notation that we use for context-free grammars, okay? So for context-free grammars, we do not use the clean star operator. We do not use the either or. So of course, when we did automata, we use the plus for either or, but there are also some authors who use this to mean either or. So this, in this context, is the either or for regular expressions. So we say either A or B, we'll write it as A plus B, okay? So we cannot use that, or we can't also use parentheses inside CFGs. So we should not mistake. So for example, this is wrong because now this is a production, this is a CFG, so you can't say A star B. But when we want to now express A star B as a CFG, as a production in the CFG, we know that here we're basically saying A is being, we can have multiple repetitions of A and a final B. So that means here, this needs, in the CFG, we need to convert this into a non-terminal, okay? So here we have S goes to non-terminal A, and then a final B, and then I would have another production that tells us how to rewrite A into A star. Okay, so the recursion happens by creating an non-terminal and showing how you build onto it as opposed to using the clean star operator. So that's what we've said. So we've introduced a new non-terminal A. And because now here we're trying to show A star, which is multiple repetitions of A. So we introduce the recursion this way. I hope you remember all this. So A is written as A, not terminal A, which means that every time you use this rule, you're appending an A, which is the equivalent of using the clean star operator. And then, of course, we put in the other production for A is written as a lambda, which allows us to delete the non-terminal, because then if you don't have this, you'll keep recursing and you'll never stop adding an A, meaning that the grammar will never accept anything. So we use this too, and let us delete the last non-terminal that we don't need to rewrite. So for instance, if we have this, so if we want to now, this is what we have as our regular expression, and we want to convert this into a CFG. So we're saying we can't use the either or, we can't use the brackets, we cannot use the clean star operator. So in this case, which non-terminal do we need to create? Mutinda Elvis. For the CFG, which non-terminal do we need to create? So Hansel says BNC. Why BNC? Hansel, why BNC? Why aren't you talking? Somebody who can talk? Jerry?
Want to select the B will point to a terminal state of B or a non-terminal state of C, and then the C will point to a non-terminal state of C and a terminal of C or lambda.
Okay. So there are many ways to do that, including what Jerry has said. But in this case, We would then create a new non-terminal X that takes care of the bit that has these operators. And then now we also need to rewrite this. Okay. So here we can say it goes to either B or C star. If we look at what this, because this thing, if we start from here, they're saying we have S goes to A. So A is a terminal symbol. And then concatenated with B or C star. So we've now created an non-terminal X that takes care of the B or C star. So B is a terminal symbol. So we'll just need to sort that and then deal with the recursion of the C. So in this case, we do that. X goes to either B or C star. Then we create a terminal to cater for the C star. And then we have C goes to C or lambda, I think what Jerry said. Okay. So this is just a refresher because this is stuff we already did in year 2. So all we're basically saying, do not confuse the notation for regular expressions with CFGs. CFGs are a totally different notation. So even as you implement your parsers, of course, you're going to be using CFGs in the strict sense of CFGs. And in fact, we use the Baker's null form, which is the BNF, which is what I'd ask you to use to define your mini grammars. So CFGs have many utilities over and above CFGs for natural languages or for programming languages. You can have them for specialized languages. So this is an example of a CFG for understanding or generating chemical compound names. And this would be such an interesting project to imagine if you're writing, coming up with a program that's helping chemistry students study, and you're creating like a quiz and they have to write something. So you want to be sure that the answer is correct. Yeah. And because it is something generated, you can't always have a list of all the possible chemicals that you could make, especially you're trying to test them by even giving fictitious combinations of chemicals. So something like this can just help check that, for instance, the number of ions, have they gotten them right? Because you have a way to just cross-check the format. Yeah, so these are utilities beyond what we are used to. So this will be a CFG for chemistry. And you can imagine that would be an interesting project to do. We are very familiar with CFGs for programming languages. So in this case, we have a non-terminal as given. I remember that for each non-terminal, we must have a production that shows how to rewrite that non-terminal. So in this case, a block is written as either a statement or statements in between curly braces. In statements goes to either epsilon, that's lambda, or a statement followed by statements, and so on and so forth. Then we have the blocks. And I'm sure you already have some of these in your mini grammar specifications. So just as a refresher, we use capital letters, usually at the beginning of the alphabet to represent non-terminal, so like A, B, C, D, etc. We have lowercase letters to represent terminal symbols. And then here we're going to introduce the lowercase Greek letters to represent arbitrary strings of terminals and non-terminals that are combined. So in something like alpha, then you know it is a string that has both terminals and non-terminals. So before we're calling them working strings. Yeah, so that's a working string that has both or a partial derivation. So for instance, you might have an arbitrary production written as A is written as omega, or A, T shows that we have a non-terminal A followed by a terminal. Or you can have an arbitrary production such as B is written as alpha, A, T, omega. So saying that there's some omega and there's some alpha that is having a combination of terminals and non-terminals. So this is to help us, especially when we're doing our proofs. So you all remember what derivations are. And it's basically the sequence of steps that we apply from the start symbol to get to just a string of terminal symbols in a given sequence as governed by the grammar. That's what we call a derivation. And remember, we use the double arrows to distinguish between the grammar rules and the derivation, applying the rules to the string. So we say that a string, a working string of the form alpha, non-terminal A, omega, yields the string alpha, gamma, omega if and only if there's a production in the grammar where we can rewrite A as gamma. Okay? And you say that if alpha yields beta, then we write it like this. Because we're saying A has been derived, you get beta by deriving from A. And you say that alpha derives beta if and only if there's a sequence of strings where you start with alpha and you have all the sequence of strings and we end up with beta, which we also express this way. So repeated derivations transform alpha into beta. So these annotations we'll be seeing as we especially talk about the algorithms for parsing. So that's why we are reintroducing them here again. The other thing we talked about were derivations. So we have different types of derivations. We talked about leftmost derivations. We also talked about rightmost derivations. So can somebody remind us what was the leftmost derivation? Anybody who remembers what was the difference between rightmost and leftmost derivation? Anita, Terry, what do you remember?
The leftmost derivation has to do with expanding the non-terminal on the leftmost side of our expression.
Yeah, correct. And rightmost would be the opposite. That every time we have to rewrite a non-terminal, we choose the rightmost. That gives us a rightmost derivation. If we choose the leftmost, that gives us a leftmost derivation. Thank you, Anita. So in this case, this is an example of a leftmost derivation. So here we are starting from statements, and we write statements using statements. So that gives us that. Then the next one we write now is statement, and we write it as expression semicolon. Then again we write expression, and we've chosen this production here, expression equals expression. Then we write this expression into ID and so on and so forth until we've written all of them. And we said it helps when you choose either a leftmost or a rightmost, then it's very clear how to build your parser. You know, because you can imagine if you're building a parser and anytime you're deciding should I do left or right, it becomes too ambiguous. Yeah. So we see actually for the parsing strategies, they assume either a leftmost and just stick with it, or they assume a rightmost and just stick with it. Yeah. So it's good for us to just remember what leftmost and rightmost mean. So we already said this. And we're saying this becomes very important when we start building our parsers. Now, there's a notion of related derivations in the sense that for some grammars and some strings, whether you do a leftmost or a rightmost, you still end up with the same parse tree. But there are other grammars where you end up with different parse trees. If you do a leftmost or a rightmost, yeah? So in this case is an example of a grammar where for a given string that is int times bracket int plus int bracket, a leftmost or a rightmost derivation yields exactly the same tree. So you can see this is the leftmost. We kept writing the leftmost, leftmost, leftmost. Here we've written the rightmost, rightmost, rightmost. And we would draw the tree for that. We end up having the tree is the same. Okay. So derivations encode for us two different pieces of information. The first is what is the sequence of productions that we have applied from the start symbol to get to the terminal string. And the second thing is the order in which we apply them. And the order really does matter, as we'll be seeing as we go ahead. So you may have multiple derivations using the same productions, but using them in a different order. So, and this is a very good example that we've used the same derivations, the same production rules, but the order in which we use them was different. Yeah, so here we first did bracketed E, whereas here we wrote E as int. That's what we're basically saying. The order is different, but we've ended up using exactly the same productions. So let's see how we build our parse trees. So we'll start with the non-terminal symbol. And remember, when we build our parse trees, the nodes become the non-terminal symbols until we get the leaves as the terminal symbols at the bottom of the tree. Then, if the next derivation, we write E as E of E. We then need to create two nodes with the operator. Yeah. Then we rewrite the E again as int. So it means we now need to write this E as an int. And here we are putting it as a leaf because int is a terminal symbol. We don't need to rewrite it, so we don't have a node for it. So here blue are nodes. And then we have times, also is an operator, is a terminal symbol. And remember now these are the tokens that is received from the tokens that have come from the parts from the scan. And then we have E times bracket. So we're gonna write E as bracketed E. And then we write E as E of E, and so on and so forth. So as we have a derivation, we are adding a level on the tree, or we are adding something, we are building our parse tree. So each derivation yields something on the parse tree. And I need you to start visualizing how you're going to build your parsers. Yeah, because ultimately you have to build a parser that, given a token string, is able to check how we have moved from the start symbol of our CFG to us, to check whether we've consumed all the tokens that came from the scanner to say yes, we've had a successful parse or not. Yeah. So in fact, the bigger work for this project is, for this course, is on the parser. Remember, we said that the parser is really the heart of the compiler. It's the one that basically controls the compilation process. So it's important that we really understand how parsing works. So this is an example of now doing the rightmost derivation. And I'll just move quickly. So a rightmost derivation, you'll notice that it still gives us the same tree. Yeah, so this was the leftmost. We used a different sequence, but it's exactly the same productions. We end up with the same tree, but we know that we did left or right. So we're saying for some grammars, a left or rightmost yields the same thing, which is what we want, as opposed to having different parse trees that now brings in what we call ambiguity. So a parse tree is a tree that encodes the steps in a derivation. We know that the nodes represent non-terminal symbols, whereas the leaves are the token string. And when you do an in-order walk of the leaves, it should actually yield the string that came from the scanner, if indeed it was syntactically correct, that the token stream follows the grammar rules. So it encodes the productions which are used, but not the order in which those productions are applied. Because when you look at this at the end, you may not know the order in which they are applied, but you're able to know exactly which productions were used. So the goal of parsing is to recover the structure that has been encoded or upon which the token stream is based. So because we are describing our language as a CFG, so the goal of parsing is to recover that parse tree for the input stream that came from the source language. Now, the biggest challenge we face as we deal with our parsers is actually, it comes from the way we define our grammars. Okay? There are many types of inherent challenges in CFGs that can complicate the parsing process. And we must understand these challenges and address them before we attempt to build the parser. Okay? So we already said that the parser is what directs compilation. And we refer to that as syntax-directed translation. That based on the CFG, the parser will ask for the next token from the lexer. If it gets the right one, then it knows it is seeing a particular production, and it continues building, and we'll be seeing actually the bottom-up and the top-down approaches that are used. You'll get to choose which approach you prefer to use, but the algorithms are pretty straightforward. All you need to do is implement them. When you have a really good understanding of how they work, it becomes a trivial exercise to actually implement them and follow them to the letter. And that way you're able to very quickly make a decision whether the token stream is a valid string as per the CFG that you define. But before we get there, then we have to make sure that our grammars do not have these challenges we're talking about. So the problems that we might encounter in our grammars, the first one, of course, is ambiguity. Then we have lambda moves or epsilon moves. We have cycles. We have left recursion, and there's something called left factoring. So we're gonna go through each of these as we're going through the course, and we'll have to figure out how to eliminate these challenges so that now we're able to apply the parsing strategies. So we've seen that there are two: there is top-down and there is bottom-up. So as the name suggests, top-down always starts with the grammar start symbol and tries to generate the token stream from the scanner. Bottom up, as the name suggests, starts with the token stream and tries to work its way up to the start symbol. So for each of them, we have to make sure that these problems have been eliminated from your grammar, otherwise you might end up in an infinite loop. For instance, if you have left recursion. So we'll go through them over time, but today we'll focus on ambiguity largely. So the first thing, can somebody remind us what ambiguity means in the context of language? Edith, what do you remember ambiguity to mean? Edith Naite.
Yes. I'm sorry, I can't hear you.
So how are you listening in the classroom if you can't hear me asking you a question? How are you following the lecture?
I think kuna shida ya connection.
Yes, Eugene.
Isn't good.
Eugene, go ahead.
It means it's not deterministic. There's no specific meaning.
Are you sure? No specific meaning or multiple meanings?
Yeah, there's multiple meanings. There's no one direct answer.
Okay. Yeah, so basically ambiguity is when we have an option. Our process generates multiple options and that becomes a headache to determine which one is the correct one. Yeah, so of course we don't want a compiler that faces ambiguity. You always want to be sure when you parse something, you always get the same thing. Yeah, so that's why it's important to eliminate ambiguity. So how do we detect an ambiguous grammar? This is just a refresher. We did this in year 2. What were the rules for detecting an ambiguous grammar? Or how did we know that? What was the condition for an ambiguous grammar? Bikuri Adrian.
I can't remember.
Okay. If you're honest, anyone remember?
I think an ambiguous grammar.
Who was speaking? Nelson.
An ambiguous grammar will generate more than one parse tree for the same input token or input string.
Yeah. So if we find a string that gives us 2 different derivations, then you know that that grammar is ambiguous. Okay, so let's quickly refresh our memories on this. So supposing that's our CFG, it's for expressions, arithmetic expressions. So we're saying E can be written as E plus E, or E times E, or into brackets, or just the int, which in this case we're calling A. And we have our expression as A plus A times A. Okay. So if we do a leftmost derivation, we have 2 options. So the first one is when we've said E goes to E plus E. Then this E leftmost goes to A. Then this becomes the next leftmost. We write it as E times E. Then leftmost E goes to A. We have the times, and E goes to A. So it's given us this tree. You could also then choose to first use this production. So for this tree, we use this production first. So you could also use this production, and that's the next example, where we said E goes to E times E. Then we write this E as E plus E. Do the next leftmost derivation. So here we have two leftmost derivations for the same string and the same grammar. And that was one major definition of ambiguity. Yeah, so we have two different derivation trees, and they're both leftmost derivations. And you can see why we're getting the two is because the top level here, you can either say E plus E or E times E. There is no way to prevent one from being executed over the other, or there's no precedence or anything. So this definitely is an ambiguous grammar. So it is ambiguous because we have shown that we can generate two derivation trees for a given string. Yeah. So the formal definition of ambiguity was if we have two leftmost derivations or any two derivations for the same string, then we say that that CFG is ambiguous. Okay. So of course, the bigger challenge here is how do we determine this string? You know, you may choose a string which doesn't give ambiguity. So it's almost like you have to keep try and error until you find one string that you can generate more than one per string. And we see that's also a challenge. So when a grammar permits several different syntax trees for the same string, then we're saying that that grammar is ambiguous. It is desirable that the grammars we're using to build our compilers are unambiguous, so that we have a deterministic output, that it always generates the same structure for the same string. You can imagine if you have a compiler, 1 minute you give it A plus A times A, and it gives you a different result. The next time you run it, perhaps it randomly chooses one of the other productions and gives a different answer. So that would be a very bad compiler. And that's why we must eliminate ambiguity, so that we are always sure that for the same string, we'll always get the same structure. That's the same parse tree. Yeah. So the good thing is that we can eliminate ambiguity by rewriting the grammar to remove the ambiguity. And remember, we call this hacking the grammar. Yeah. So we can rewrite it so that it generates the same set of strings each time that string is presented. So another way, especially for natural language processing, is that you can have external rules that help you to choose between different meanings. And you see, for instance, for natural languages, especially now when there are things called reference, like when talking about pronouns, they usually can be very ambiguous. You know, when you've introduced very many nouns and then you're saying he, then, and she went or it really generates a lot of ambiguities if you're trying to parse natural language sentences. And sometimes it's not very easy to hack the grammar. So in such cases, then you define external rules that determine for this particular type of ambiguity or this kind of sentences that are option, then choose this one. Yeah, but of course for the compiler, we don't want to go that route. For the compiler, we just want to make sure that the grammar we use is ambiguous. So we have to rewrite it to eliminate ambiguity completely. So here I've already said that if we're using the notion that we must have, for us to know that a grammar is ambiguous, we must identify a string for which we can generate more than one parse tree. That is actually a very difficult problem to do in terms of an algorithm. And we say that that is a problem which is known as undecidable, which means that there is no method that would work for any grammar or for all grammars to answer, is this grammar ambiguous? Yeah. And because it is, there's no formal way to do this, then the solution is to simply just do it manually. As a human being, you look at your grammar, figure out if it's ambiguous, and you fix it. Yeah. So in many cases, it's not difficult to detect and prove ambiguity, but there are hard and fast rules that allow us to suspect that this grammar could be ambiguous. So for instance, if you find a production of this form, a non-terminal rewritten by a non-terminal and some string, and that's in non-terminal, so n, you can be sure this is ambiguous, like the example we've just seen for E plus E or E times E. So there are hard and fast rules that if you see this kind of production, then you almost know that that grammar is ambiguous, and it becomes easier to generate a string to prove. So we're going to see over time how to really eliminate ambiguity. So this is a slide actually from the year 2 course when we did ambiguity, and we asked, why do we care about ambiguity? And why we care is that if we have these two trees and we assume that A takes the value of 2, so which is the correct tree? The one on the left or the one on the right?
And on the left.
Yeah, the one on the left, because we want to do times has a higher precedence than plus. So here we want to first make sure before we do the plus, we get the result of this subtree by doing the times, and then we add the result of times to this A, as opposed to the other way around. Yeah. So we do care about ambiguity because in this case, if we just try to substitute those values, the first tree will give us 6, which is the correct answer. 8. So you can imagine if you have a compiler that decides, okay, for some reason I'm going to use this tree because both of them are actually syntax giving us a value of 8, the other is a value of 6. Really ever want to find? This happens. Yeah, so that's why we want to follow, for instance, for arithmetic. Yeah. So very bad for programming languages. And so we'll just go through how to do that. Because we have, so these two expressions are what are giving us that option, which generates the ambiguity. So in this case, we have the grammar and introduce a new non-terminal that takes care of one of the expressions. You now fix them in the order that you want the operations to happen. So in this case, multiplication has a higher precedence. So you make sure that before you can do the plus, you have the results. This T has to be rewritten, and it is written by doing the times. So once this is written, the E plus can be completed. So that becomes the new and ambiguous grammar. And in this case, for the same string, A plus A times A, we only have one possible pass tree. And it actually is following what we want because it means we first have to complete the times to get the result for the addition, which means we have rewritten the grammar to respect the mathematical rules. So even for statements, it's possible to have ambiguity. And as we're going through this, I need you to just think through the grammars the mini grammars that you specified. And the first thing, of course, you're going to go and do is check whether your grammars as specified are ambiguous. And if they are, then you will have to hack and remove the ambiguity. So this is an example of an if statement. So if statement can be written either as if expression then statement or if expression then statement else statement. Okay, and this is also an example I pulled from the year 2 slides. That it can give us those two different trees. And I want somebody to tell us what is the problem with this. Why are we saying the ambiguity in this case is undesirable? Anyone?
I can try.
Okay.
Yeah. So for the diagram above, when expression 1 is false, there's a chance that either statement 1 or statement 2 will run. And for the lower diagram, if expression 1 is false, only statement 2 can run. So there's ambiguity there.
Yeah. That even statement 2 over here is dependent on the truth value of expression 2, whereas it is dependent on the truth value of expression 1. So really would not want something like that. We want to always be sure that the logic as the programmer intended always works based on how the grammar has been structured. So we need to really eliminate that ambiguity. So this is another example for ambiguity. So we have 2 minus 1 plus 1. And in this case, you can see, do I have the example of the grammar? Okay. So in this case, the challenge here is that the operators are of the same precedence. So minus and plus have the same precedence. So if we do not write our grammar in a way to enforce associativity, then we introduce ambiguity, because then you could either operate, the parser could actually build the tree to enforce, assuming 2 minus 1 is into brackets and you get this tree, or 1 plus 1 is what is bracketed, or the addition is done first and you get this tree. Of course, these two yield different answers here. So this is another example of ambiguity. So you've seen where operator precedence is not enforced, and also where we don't enforce operator associativity, so that we eliminate ambiguity. So in this case, if I was to ask you which one should be the correct one?
The first tree is the correct one.
I didn't get that. And who was speaking? So Adrian says the one on the right. Nelson, what did you say?
I think the one on the left is the correct one.
We have 2 different answers. So Nelson, can you justify yours? And Adrian, can you justify yours?
I think because the addition and subtraction have the same precedence, so you don't have to.
Okay, let's have Adrian. I think Nelson has an audio issue.
In the order of operations, addition comes before subtraction.
Huh?
Addition comes before subtraction.
Says who?
Order of operations.
Huh?
The order of operations.
Okay, I can't really hear you. I'm a bit concerned. You guys seem to be taking this class from very noisy areas. I even understanding what we are talking about, because everybody who's unmuted themselves in a very noisy space. Why can't you find quiet areas to have your class, your online class? Nelson?
The interference.
Huh? Or
It's
in
the
the
interference
or
from the numbers. I think
addition and subtraction have the same precedence. So I think the one that appears first is the one that should be executed first.
okay. So of course, now this brings us to the next topic, which is operator associativity, which I hope you have covered either in operating systems or somewhere, that different programming languages define the associativity for operators that are of the same precedence. and the different types of associativities. I know what Adrian was talking about. We all were taught BODMAS, that addition comes before subtraction. But when you're building our compilers, now there's a notion of associativity, which is what is actually implemented. So operators are either left associative, right associative, or non-associative, okay? And left associative means the operator binds from the left to the right. So in this case, if you have A plus B plus C, it first starts with the leftmost operator and then does the right one. If it's right associative, for instance, exponentiation, you first do B raised to C and then A raised to the result of this. Then the ones that are non-associative means it's illegal, it should not be allowed. Of course, I don't know if it's Python, I know C++, something like this is not allowed, but there's some languages like I think Python that somehow, I don't remember which one is which. But what we're saying here is that each language then defines the associativity. Of course, most of them are going to be guided by the rule of arithmetics, but by and large, we actually end up using left or right associativity for operators of the same precedence. The other thing we'll be looking at is we talk about recursion, and this is what we talked about, left factoring, left recursion. If the recursion is happening to the left of the non-terminal, then the operators bind to the left. If the recursion is on the right, then we use right associativity. Yeah. So here, what's important is to note that for whatever programming language the compiler has, or rather the grammar specifies, operator precedence first, and then associativity for operators of the same precedence level. And this is a good time for you to go read up on your favorite programming languages. Just confirm that you understand how they define associativity, especially. And then also now in your own mini grammar, you have to decide how do you want the operators of the same precedence to behave. Okay. So let's look at an example of operator associativity. So we have this grammar has 6 productions. We have plus, times, minus, division, etc. So we're using this grammar to describe arithmetic expressions, and num in this case just describes all integer tokens. And our parentheses are also terminal symbols. So operator associativity describes the operator that an operand binds to when it is between operators of the same type. So we have an expression here, 3 minus 5 minus 4, right? So even in the case of BODMAS, it still might not help us here because now we have both of the operators are the same. So in this case, if we do not specify associativity, we will have an ambiguous grammar because it can give us 2 trees depending on which one it binds to first. So in this case, if it first does something minus 4, and then that's something expanded 3 minus 5, we get this tree. Or if it does 3 minus something, then that something becomes 5 minus 4. We'll get 2 different answers. I think this will evaluate 2 different results. So we would not want to leave operator associativity undefined, right? So if that's what we're basically saying, that if the associativity is not specified, then that grammar is ambiguous. So this tells us that we need to specify associativity to ensure that we don't generate ambiguous grammars. So for the operator for subtraction, typically, even addition, associativity is usually left to right. So the way this grammar has been defined, we assume everything is left associativity. Is the operators associate to the left when they're within operators of the same precedence? Or rather, an operand is between operators of the same precedence. It could be the same operator, or it could be like now plus and minus, or division and times. So we need to hack the grammar also to just ensure we enforce the associativity we want. If you're creating your own crazy grammar that does things opposite from math, then you have the chance to hack the grammar to implement what it is, the policy that you want. Yeah. But of course, for useful compilers, we follow the natural laws of arithmetic. So in this case, if we have something like this, we're saying our original grammar, we have the expression, can be written as expression, operator expression, then can go to int, and then with the brackets. If we hack it this way, it says the start goes to the expression. Then now, this is where the ambiguity is coming in. So we hack it to ensure that we've given some precedence, or rather we've specified the associativity. So in this case, we rewrite expression goes to int. So what does this mean? We've actually said that it will always bind left, because before you do here already, you've taken to a terminal symbol. So it means this has to be evaluated first, so to get the result from here to add to this, meaning that you said this operator is always going to be left associative. So if you hack your grammar in this case, all operators are left associative, which is also a problem because we've not separated maybe the times and the addition. Yeah. So for example, we now have this pastry 2 minus 1 plus 1. We know that these are the same precedence. We can only have one pastry because we're saying expression goes to op int. Then now, so that means the 1 is one that is here. Then the expression has to first evaluate 2 minus 1. So you have 2 minus 1. So we'll never be able to generate something like this. Okay. So that is one way to hack the grammar to enforce left associativity, if that is what you want. But then, if you just do that, it means whether you have times or minors or whatever, if you've made all of them left associative without separating them for precedence, you still have a problem. So the other thing we also have to think about as we're hacking our grammar is to cater for precedence as well as associativity. Okay, and I think we're releasing something like this. So in this case, if we have the same grammar that we've used and we have the expression 3 plus 5 times 4, we don't want to have the two options. Yeah, this one we know we want to enforce that. We first do the 5 times 4 and then do the plus. Okay. So the same thing, if we don't specify the precedence, we'll get ambiguity. We know that multiplication should have a higher precedence than addition, but our grammar does not specify this. Yeah, it's just focused on left associativity only, but we've not specified precedence. So we need now to use both precedence and associativity rules to be able to select between the pastries. So what we need to do is now hack the grammar to enforce the precedence and associativity that we want. That's what we mean by saying it should be expressed in the grammar itself. So at this point, I want you to just think through the mini grammars that you've defined. And that will be the first thing you'll do after today's class, is to just go and check whether, in fact, your grammars are ambiguous. And we already seen the different sources of ambiguity. It could be from precedence, it could be from unspecified operator precedence or operator associativity, or from repeating terms where you have so many options, E goes to E plus E, or E goes to E times E, etc., etc. Yeah, and then you now realize that the first thing you have to do is hack your grammar to eliminate all those sources of ambiguity by enforcing now the operator precedence and associativity rules. You express them directly in the grammar. So this is an example of how we can hack to avoid operator precedence violations. So in this case, we are saying if our grammar just looks like this, we have the operators, we've not given any precedence, we're just saying operator goes to either plus, minus, times, division. Then you have our integers and you have open and close. Here we've said this is enforcing left associativity because this has to be done first. So this operator will first have to bind on this side. So all operators here are associating to the left, which violates the precedence between division and times with minus and addition. So this is allowing us to have 2 minus 3 times 4 associating like first, as if we first must do the minus, then we do the times. So we want to hack this, and how we do that, now we're giving you the tips. Once you find your grammar is ambiguous in terms of precedence, this is what you're going to do to remove ambiguity from lack of specified operator precedence. So the general idea is that you create precedence groups, and we group our operators into those levels. So for instance, we have the plus and the times and division would be in a group on their own. We have plus or minus at the next level, and so on and so forth. And then you decide which one, what is the precedence ranking. So of course we want times and minus to bind first, and then plus and minus. Sorry, times and division should go first, and plus and minus should go next, etc. So once you've done that, you create now a non-terminal for each precedence level. So in this example we're going to show, we'll have created a term for the first precedence level for times and division. Then we'll create a new non-terminal for plus that binds to plus and minus. And then within each of the groups, you can then now decide to make your operators either left or right associative. Yeah, if you always want them to be right associative, then you will hack the grammar to ensure that they're right associative, and we've seen how to do that. If you want them to be right associative, then the left-hand side should bind to a terminal. The right-hand side of the operator now should be a non-terminal. Left is the opposite. And once you do that, basically, you've hacked around precedence. Note that this idea can generalize for arbitrary levels of precedence. So supposing you have maybe other operators you want to talk about, maybe you want to decide that brackets don't come first, or they come higher than times, and which is actually what happens. Then you would create another level for that precedence for brackets, or whatever it is that you're trying to do. So once we do that, so let's see how that has happened. So we've created two precedence levels. We've grouped operators into two. So we have the add operators, that's plus and minus, is one level. Then we have the second precedence level, has the times and the minus. So we've created two. We said the thing is to create two non-terminals, or a non-terminal for each level. So we have add op is the non-terminal for this level. Malloc is the non-terminal for this level. Then now when we have our grammar, we have the start goes to expression. Now expression goes to add op term. So here we are saying now this is the first level, you must do addition. And then this term, because we want it to have it has a higher precedence, now this is what should go to the higher precedence, because you must, before you can do this operation, this must be evaluated. And then term now takes the next level of operators, that is the malop. Yeah, so once you do it this way, always then this level will always be done first, so that they return a result for this second level, which now has implemented precedence. And then within each level where you're doing now add up, you decide whether you want it to bind left or right. So in this case, with our new grammar, if we have 2 minus 3 times 4, remember before we had not enforced precedence, so we could get a tree where you first do the minus, and then the result of the minus is what goes to be an operand for the times operator. But in this case, if this start goes to expression, we're saying expression add up term. So before you can do add up, you must do malloc, yeah, which means you first have to do times, and then the result of the times is the operand for the add up operator. Okay. So now we have this, it is now non-ambiguous, which is what we wanted. So I think that should help you figure out. So that would be the first thing, is go look through your grammars, especially where we are having the if statements or nested statements and arithmetic expressions. Typically, those are the areas where we get ambiguity, and figure out. It's the same thing with logical operators. Do they have precedence, like and, or, all those?
Yes.
Yes, Craig, I didn't hear you.
Yes.
What is the precedence for logical operators?
I think and is higher. I think and is higher. I'm not sure of the order, but I know there's a precedence.
I also cannot remember. So
Yeah.
that's also homework for us to go check if you're having logical operators, what is the required precedence, and if your grammar has them, has it enforced the correct precedence? If their logical operators are the same precedence level, should they bind left or right associativity, and hack them accordingly? So I think in summary, we are saying ambiguity is very bad. We want to remove it. so that we always get one pass tree for a given string, and our compilers always generate the same structure for the same input from the source language. Okay. So the other thing we want to now talk about is the abstract syntax trees. We've talked about pass trees in general. So a pass tree is referred to as a concrete syntax tree, which basically shows exactly how the source language was derived. And that's what those are ones we've been seeing. But we'll see that for compilation purposes, what is more useful than the pass tree is what is called an augmented pass tree, otherwise known as an abstract syntax tree. And the abstract syntax tree adds, first, it retains only the essential structure of the input, but also does some augmentation that is useful for the eventual target code that we're going to be generating. Okay. So how do we build the AST? So we're saying as much as we're building the pass tree, what we want to actually build in practice is the abstract syntax tree. And what we do is that we define what are known as semantic actions. And a semantic action is a piece of code that is written to be executed for each time a rule is applied, a syntax rule, a production of the grammar is applied. Then there's some code that is executed that has some semantic actions. So as the input is passed, in other words, as we're building that pass tree, we're also executing the semantic actions and augmenting that pass tree with that additional information. Yeah. We'll be seeing that the order of code execution is based on the parsing method. The next topics will be on bottom-up and top-down parsing, which will help us understand now the order in which the tree is built and the order in which the productions are applied, which also has a very significant bearing on the meaning of the eventual meaning, the output of when you generate the target code, the values you will get for the code that is being called. So let's see how we do the semantic actions. So remember, we said the semantic actions is basically a small piece of code that is associated with each production in the CFG. So every time that a production is called or is used to rewrite a non-terminal, that piece of code is executed. So in this case, we have our grammar productions here as before. Let's take the first one. E is written as T plus E. So we are saying these are the associated actions to be, these are the semantic actions. So we're basically saying that the value of the first expression, E1.val, will be computed as the value of T plus the value of expression 2. Very simple. Basically saying E1.val equals T.val plus E2.val. A production of this form, the associated semantic actions, is basically assigning the value of E to the value of T. So E.val is equals to T.val, and you do the same for everything. So you can guess from here what we're trying to do is to have, to be computing the values, the actual values to be tied to these expressions as we build the tree, so that we have intermediate results that we can keep reusing, as opposed to just building a pass tree where you don't even know much about the operands that you have. So let's look at an example. So if that is our token string coming from the parser, from the Lexa, these are the entries that we have in our simple table. We have an int with the value 26. We have a token multiplication, another token of type int with the lexeme 5, etc. So once the parser gets the first thing, so in this case, int, if it calls this rule, which one it has called this rule, t goes to int. So the semantic actions that will be called is that the value of t is basically the value of the int. So you can see you've basically copied the value from the int is copied to. Now we know the value of t is actually 5 as well. And then the next production that is called is t goes to int times t. So we have int times t. So times remains, then we know this int is 6. So the semantic actions for this show that the value now of this t that we've built as a node will be the value of the int times the value of t, which will just be now 26 times 5, and that becomes the value that we associate with t. So you can see why this is important, and it becomes very clear why this is important now when we start generating the target code, that you don't have to start going through the parse tree again to come and figure out now what is the value of t. So as we're building the tree, we're also working on the semantics, where we are now saying, now we know the value of t at this point is 130. We sort of started evaluating what is really happening. And then the next thing we have, we call this t goes to int, and we basically are copying the value using the semantic action. The value of t is assigned to the value of int, which is now 7. And then finally, we have this expression goes to t. So the value of the expression is the value of t. So we basically copied the value of the expression is the value of t. So we have a 7 there. And then finally, the value of e, when we have e goes to t plus e, is you add the 2. So the value of e will be t plus e, which is 137. So by the time you're done building the parse tree, you also have the value of that part of the tree. You can see that this is much more useful than just having the structures that we were having before. Let's go back here. It's when you just have something like this, yeah? If you just have this, you can imagine the next stage of semantic, you still have to go through to come and propagate the values up. So the augmented syntax tree really helps in dealing with this, so that we are a bit more intelligent in our parsing. So these are other examples of semantic actions when you're dealing with strings. So something like R goes to R or S, then it shows you what to do. So in this case, depending on your grammar, you figure out what are those semantic actions that help you to propagate the values. Because ultimately, you see, you have to generate some intermediate representation. And for that, you have to use the actual values. When you're doing the intermediate code, we don't now use variable names. We basically just be using the values as we have computed them. So in summary, today we've talked about syntax analysis, what it is, what the goal is, and you said there are two goals. One is to uncover the structure, the underlying structure as per the CFG for the token stream that comes from the lexer, and to generate syntax errors where we cannot come up with the structure from the CFG. And we have already intimated that there are many challenges that can complicate syntax analysis. We've talked about ambiguity, and today we really extensively talked about ambiguity, and there's different sources of ambiguity. Could be lack of specifying operator precedence, or associativity, and just the way we write our productions. And we've said that for programming languages, ambiguity is totally unwanted and would have to hack our grammars, rewrite them to eliminate any source or form of ambiguity. The other thing we've said is that there are many other grammar challenges which we'll be looking at in due course. We talked about left factoring, left recursion, lambda transitions, and we'll be seeing those as we progress through the parsing strategies. So we figure out why it's a challenge and how to remove it from the grammar. Yeah, and then lastly, we introduce the notion of abstract syntax trees that we associate semantic actions with each production, so that by the time of parsing, we also have values for the different sub-expressions, which makes it faster. Remember, the goal of building a compiler is to reduce the compilation time. So as much of the things as you can do concurrently and to avoid many repeated passes. Remember, I talked about a passes, how many times you go through the source code to come up with the final target code. If you want to reduce that, then there are many actions you can do as you do other things. So as you're building the syntax tree, the parse tree, you can augment it with semantic actions so that you don't have to go back again to compute the values of the expressions. Okay. And that brings us to the end of this class, which was basically an introduction on syntax analysis. So the next time, we are going to be talking about now the different strategies for parsing. We'll start with top-down parsing, then after we're going to do bottom-up parsing. Most probably, you're all going to implement top-down parsing. it's the easiest to do if you're building your syntax analyzer by hand. If you're using a parser generator, then you could try out bottom-up parsing, but it's a bit more complicated to implement. But you can just basically start reading about this. So we're going to look at all these backtracking parsers, predictive parsers, and LL1 parsing as what we're going to be talking about. Did I hear somebody's hand up? Okay, so now tomorrow we have the session where we go through your scanners. So I hope you're ready. I think you're supposed to have submitted them. Has the time passed? I know it's today at some point. Where are we with respect to our scanners? Anyway, I hope you're ready for tomorrow's presentations. So I'll randomly pick on a group to start. You will share your screen and you will perform some actions based on the grammar you specified and the tokens you specified, and want to see the output. So I will be giving you random things to do on the screen. So make sure you're ready for that. It's a critical part of your assessment. As you said, the bulk of this course is based on practical work. And all your team members must be present for the presentation. And make sure you are on time, because if you call your group at 2 and you're not in, you will wait till the end. And if the end happens before we reach you, then we will count that you are not there. So let's end there. We meet tomorrow afternoon. It will still be a virtual class tomorrow. Thank you, Hansel. Bye, everyone. And as I said, I'm taking the attendance using an extension. So if you've not been in class for at least 80% of the time, I count it as not having attended, unless you have a very good reason why you dropped out of the class. All right, have a good afternoon.